All right, now we're going to look at section 4.2 out of the book on null spaces, the column space, and linear transformations. Now again, these are some ideas that we've seen before, but what we're going to do is we're going to present them slightly differently and a slightly different way of thinking about them. And we're going to present them also in terms of linear transformations and see how that gives us a slightly different idea around them. So first off, recall a null space. We talked about a null space before being all of the things that when you multiply by a matrix turn into zero. So here's the mathematical definition of it. If we have an m by n matrix, so m rows and n columns, the set of solutions to Ax equals 0 that satisfy this, it's all of the elements in Rn such that Ax equals 0. That is the mathematical definition of the null space. And the null space is denoted by NULL or sometimes just by NUL of A. Okay. You can also think of this in terms of a transformation. Remember we spent a bit of time on saying how matrix multiplication and linear transformations, there are a couple of things that have different definitions, but there is this correspondence between them, that a transformation has a corresponding matrix where the transformation is just the matrix multiplication and vice versa. So again, matrix multiplication and linear transformations are kind of two faces of the same thing. If you think about this as a transformation, this matrix A is giving you a transformation from Rn into Rm. That takes you have n variables, it takes an n-dimensional vector and it turns it into an m-dimensional vector. So your transformation is going from this Rn into some subset of Rn, and T is going into there. The null space is everything in your first set that turns into 0. So Rn, what you have over here is it's a subset, a subspace of Rn. There is a 0 vector in there someplace. And it's all of the things that map onto the 0 vector. You know one of them is going to be the 0 vector itself. 0 maps onto 0. But there may be other things that map onto that 0 vector. All of these things that map onto 0, that turn into 0 when you do your transformation, that is the null space of your transformation. This leads us to Theorem 2. Now, in the previous section, we talked about subspaces. Theorem 2 says that the null space is a subspace. So remember, a subspace satisfied 3 conditions. Those 3 conditions are all satisfied by the null space. So the null space of a matrix, in other words, the things that when you multiply the matrix by this vector turn into 0, is a subspace. Equivalently, the set of all solutions to the system Ax equals 0 of m homogeneous linear equations in n unknowns is a subspace of Rn. So this is saying that you have an m by n matrix. So we have m rows and n columns. What this is doing when you do the multiplication, Ax, you have an n by 1 matrix. So this is part of Rn, and it transforms into an m by 1 matrix, which is part of Rm. And everything on the left-hand side that turns into all zeros on the right-hand side, that's your null space. This theorem says if you take all of those things, collect them all together, they are going to be a subspace. So why is that? Let's take a look at this proof. Remember, a subspace has just these three properties. It's living inside of Rn, so we know that Rn is a vector space, so we just have to show the three properties of a subspace. And do they hold? Well, first off, is the zero vector in the null of A? So we're asking, is the zero vector in the null space of A? Or this is asking, is our matrix A times the zero vector equal to the zero vector? Of course it is. We know that multiplying any matrix by the zero vector gives us a zero vector. They may be different sizes, but it gives us a zero vector. So yes, the zero vector turns into the zero vector, so it is in the null space. Second one, if we have two elements, two vectors in the null space, then we have to show that the sum of them is also in the null space. So what does it mean to be in the null space? U and V in the null space of A, means that A times U is equal to 0 and A times V equals 0. But what about A of U plus V? Well, this is matrix multiplication, so we have some of the properties. We know that A of U plus V is equal to A of U plus A of V. That was a distributive property of matrix vector multiplication that we saw back in chapter 1. But AV, or AU, is equal to 0. AV is equal to 0, so A of U plus V is equal to 0. So U plus V is another vector that turns into 0. Done. It satisfies the second condition. What about the third condition? Well, U is in null of A. That means that A times U is equal to 0. So now we have to show that since U is there, is C times U in there? So what about A of C times U, where C is a scalar? Well, again, using those properties of matrix vector multiplication, A of C times U is simply equal to C of A times U. And we said that since U is in the null space, A times U is 0. So this is equal to C times 0. Any scalar times a 0 vector is equal to 0. So yes, CU is also in the null space. So all three properties hold. So that means the null space of A is a subspace of Rm. So that is a proof of the theorem, showing that the theorem is accurate. But now here's an example. We're going to find an explicit vector description of the null space of A. So in other words, what does the null space look like? Well, we've done a little bit of this stuff before. So we've seen that if you want to find out the null space, what do? You find out everything multiplied by that vector that turns into 0. And we've seen how we can do this using variables and equations. And part of it was taking our matrix and row reducing it. Well, I've made that a little bit easier. Rather than going through all the row reduction, I'm giving you the matrix when it's row reduced. So if you take your matrix A, do all the row reductions, turn it into a row reduced echelon form, you are going to end up with this matrix. So now let's convert this back to equations. So each column represents a variable. And if you look at this, we have x2 is a free variable, x3 is a free variable, and x5 is a free variable, while x1 and x4 have pivot points, so they are basic variables. So if you remember how this works now, we can turn these equations into a parametric form of the solution. So let's take this and write it out as equations. The first row gives us x1 plus 2x2 plus x3 plus plus 4x5 equals 0. The second row gives us x4 plus 4 over 3 x5 equals 0. And that's it. So now let's write all of our equations in terms of, let's write all of our variables in terms of these equations. So when we write that, we have 5 variables, 3, x4, and x5. Our free variables are x2, x3, and x4, and x5. So we just write that x2 equals x3, x3, and x5. Then our basic variables, we write in terms of our free variables. So x1 is equal to negative 2x2 minus x3 minus 4x5, and x4 is equal to negative 4 over 3 x5. So there is our equations written in, or there are variables written in equations in terms of our basic variables. So now what does this give us? Well, I'm running out of room here, but this gives us that our null space of A is equal to, it's x2 times something plus x3 times something plus x5 times something. And what are those somethings? You get them by reading down. So the x2s are negative 2, 1, 0, 0, 0. The x3s are negative 1, 0, 1, 0, 0. And the x5s are negative 4, 0, 0, negative 4 over 3, and 1. That is the description of our null space. So our null space is the span of those 3 vectors, which is a subspace. Okay, another definition. And again, we've seen this idea before. Now we're talking about the column space. So the column space of an m by n matrix is the span of its columns. In other words, you take all the columns out, turn them into vectors, and make all of the possible linear combinations you can out of those. And it's denoted by COL of A. So in other words, if A is equal to this, and these are each of the columns, so the first column is A1, the second column is A2, and so on, the column space of A is the span of all those columns. Another way to think about it is that the column space of A is all of the vectors B, where B is in Rm, that you can get to through your multiplication. So in other words, it's all of the potential answers to C1 times A1 plus C2 times A2, and so on, up to Cn times An, that equals B. All of the possible B's that you can reach by a linear combination of the columns. That's the same as saying all of the columns where Ax equals B for some x. That's the idea of a column space, again, given in terms of a span. Theorem 3 says that the column space of an m by n matrix A is a subspace of Rn. Why is the column space a subspace? Actually, this should be a subspace of Rm. Why is the column space a subspace of Rm? Well, think about what it is. We saw before that the column space of A is the span of A1, A2, and Am, where the AIs are columns of A. Remember, one of the first things we saw when we were talking about subspaces is that the span of vectors is a subspace. So therefore, this column space is a subspace of Rm. So, just to summarize a couple of things. If A is an m by n matrix A, remember we're dealing with subspaces here. We have two subspaces right away. The column space is a subspace of Rm, m-dimensional vectors, and it's based on the columns. The null space, remember the null space is based on the number of variables in your equations. That's a subspace itself, and it's a subspace of Rn. So the column space and the null space are two very different things, and they're usually different sizes as well. Also, when we're dealing with matrix multiplication, we've talked before about how linear transformations are very similar. So you can give all of these ideas in terms of linear transformations. So if V and W are vector spaces, and you have a linear transformation, or a linear transformation from V to W is a function where the following two conditions hold. That adding two vectors and then transforming is the same as transforming each individually and then adding, or transforming a scalar times a vector is the same as transforming the vector and then multiplying by the scalar. If those two things hold, then it is a linear transformation between two vector spaces. We've talked before about linear transformations from Rm to Rn. Well, it doesn't have to be Rm and Rn all the time. It can be any vector space or any subspace. And we've seen how vector spaces are more general than just columns of numbers. If you have any two vector spaces and you have this property, then that is called a linear transformation between vector spaces. When we're dealing with vector spaces, we have the same idea of the column space and the null space, but we tend to use slightly different terms. Because if we're just talking about a linear transformation, sure, there is a matrix that corresponds to it, but we aren't talking about the matrix, we're talking about the transformation. So when we have a transformation, we talk about the kernel of the transformation. The kernel of the transformation is everything that transforms into a zero. The range of a transformation is all of the possible vectors that you end up with. So this is similar to the null space. The range is similar to the column space. Okay. And now keep in mind, again, that linear transformations, there is a one-to-one correspondence between a linear transformation and a vector space, and a matrix multiplication, but they're not always obvious. So here's an example. I'm going to give you a definition of a transformation. I'm going to do a transformation from P4. Now remember what P4 was. The set of all polynomials with maximum degree of 4 into R5, okay, where T of A1 plus A2x plus A3x squared plus A4x cubed plus A5x to the 4. Now that's a polynomial. That's a general polynomial of degree 4 or less. That equals A1, A2, A3, A4, and A5. That's a transformation from a vector space into another vector space. Now, because we aren't doing Rm into Rn, it isn't obvious what the matrix is that's associated with it. So finding that matrix is a little bit more complex here. So in this case, we would talk more about the kernel and the range of this transformation. And now give this some thought and see if you can figure out what the kernel and the range of this transformation T is. And just see if you make sure that you understand the concept of a kernel and the range and how they are similar to a null space and a column space. But because we're trying to abstract vector spaces, so we aren't always going back to columns of numbers, we've introduced slightly different definitions to help describe it. So that's the idea in this chapter of null spaces, column spaces, and linear transformations. It's things we've seen before, but we're presenting them slightly differently here in terms of kind of the abstracted vector space. And so, and instead of being tied to columns of numbers, to Rm and Rn, we're trying to think of them a little bit more generally for vector spaces.